days and come back to it. It's time. Why don't we do this? If he comes, he votes. If it's close, then maybe he can tilt it one way or the other. Anybody got suggestions for the dates of our first test?
When is the absolute latest that we can have it?
Makes no difference to me.
What all is the test going to include?
Everything up to the lecture before the exam.
Okay.
So, the longer you wait, the more is on it. You've had me. You know how this works. I don't really care. To me, it makes no difference.
Well, like next Friday.
What I'm trying to do is make sure you guys on your calendars know that you're not putting two tests at the same date or a big project in the same day with your test. So I'm trying to be kind of, I'll just tell you this, and I tell all my classes this, usually Monday tests have the overall highest average, usually. Usually Friday tests have the worst, probably because they're beat. And Wednesday somewhere in the middle. Now that's just my opinion based on, sort of as a recall of everything I've seen over the years. Friday seems to be a disaster, especially during football season. But, that said, what dates would you like to put up? So, and give me both the day of the week and the actual date in terms of calendar, like 6th, 29th, 6th, 30th.
I guess my knee-jerk reaction was Friday the 28th.
That's all right, we'll put it up Friday the 28th. This is Friday, and this is June 28th.
Yeah, so this is next week's Friday.
We'll do it this way. We'll also put up that Wednesday. I think we'll put up that Monday in case. It doesn't matter to me. And then we'll do Monday the 31st. Let's see, Wednesday the 2nd, right?
No, that'll actually be Monday, July 1st.
Oh, I'm sorry, the 1st. Monday the 1st, this is the 3rd.
Yeah.
Okay. Monday, Wednesday. So well, you said Friday, right?
Yeah.
All right, that's one date. I'm just gonna put down there's option A. Anybody else got a date? Doesn't matter to me.
Monday.
That Monday or this Monday? Which one?
Either or.
All right.
Can we not do that Monday?
Not that Monday.
Because we have a lot of common stuff due that day.
All right. How about that? Any other dates? There's not a lot of strong responses here. That's fine, we can vote on these. Now think about it. I'm not saying this class is gonna have a bomb job on Friday, but that's just been my observations over the years.
Summer's a little bit more chill.
Yeah.
Yeah, and again, this is up to you entirely. So, if you want it Friday, put one hand up, and then we're gonna count. One hand, and only one. All right, I'm seeing 1, 2, 3, 4, 5, 6, 7. I'm just saying what I see. If you want it on Monday, B, one hand. 1, 2, 3. Sorry. I'm gonna have to do this democratically. The overwhelming consensus is A, and I wish it was unanimous, but it's not. I can't do it. You know, it's just the way it is. All right, so we're gonna have it on Friday, June 20th. And somebody send me an email reminder. I mean, like today, so I can put it up there. What happens to me is, because of some of the stuff I do with the Senate chair position, I get all these meetings and things I have to be at stuck on my calendar, but they're not stuck long in advance. Sometimes says there's a change been made. Now we need to hear Friday during class or Friday right before class. Something irritating me. All right, now any questions about the homework at all? There were short wires or small loops. They all varied as sine, theta for the E field, and therefore, you're going to find out in a second, the gain's all the same. Now what I might as well do now is briefly talk about the concept of gain or directivity. Now you have to understand what antennas really do for us is they focus the beam. That's the idea. They focus energy in a preferred direction. So we need some figure of merit to go ahead and say how good an antenna is. And we use gain and directivity. First, let me just say this. Gain is the real thing you worry about, but gain, antenna gain, is equal to, its symbol is G, and directivity, its symbol is D. Gain is equal to the efficiency of the antenna times the directivity. And this is a note. Usually the efficiency, I call it EF, the book may have it as EP. The efficiency is usually equal to about 0.991. One being 100% efficient. It's somewhere, it's very good usually. I mean, some aren't, but usually they're very efficient. So when you talk about directivity, you're really talking about the gain. Now, if there's an impedance mismatch, or if there's a lot of resistance, then you can get a directivity that's very high, but a low gain because the efficiency is poor. Follow me in this class? So what is really directivity or gain? Really, I like to use the word directivity for starters. Here's how it works. If you have an antenna, general antenna, like this is a symbol. And the antenna, I know it's gonna focus the beam, it's gonna have some preferred actual focusing power. So if you take a look at the actual power radiated from this, PAV, and this is the power density, what you'd like to use is this power density and make it a function of just theta, make it independent of R, a function of theta and phi. You would like to see how much better the power density with this antenna is than that is if it was isotropically radiated, right? That's the idea. So we go and we talk about an isotropic radiator. The word isotropic means it is the same in all directions. So an example of an isotropic radiator to a high degree is our sun. Our sun radiates energy and power in about the same in every direction, every azimuth, every theta and phi, if it's the sun's at the center of the coordinate system. A star does that also. To a smaller degree, a candle does that. There's no focusing power. Now, if you put a reflective surface behind a candle, then you get, it's more or less a spotlight effect, and it focuses. So how do we actually quantify this? First, we say if we have an isotropic radiator, and it's an antenna that's isotropic, and I'm going to say this is my isotropic radiator, then at any range R, the actual average power is going to be equal to the total power transmitted by the antenna over 4 pi R squared 8R. And PT is just total power transmitted. Does that make sense? Take total power divided by a spherical surface, 4 pi R squared, that's the power density, right? All right, now when we have an antenna like this that has the same amount of power being radiated, what we do is define the directivity, and here I'm going to do it. The directivity of the antenna, it is a function of theta and phi, is defined as the actual power density, PAV, of the system with the antenna divided by the average, it's called P isotropic. So that's equal to PAV as a function of theta and phi over the total power radiated divided by 4 pi R squared. And that's the general gist of it. Now I'm going to tell you that I'm going to go ahead and make it simple in a second, but I'm going to do an example for everybody, all right? So just make sure you understand the concept. How much better it is than an isotropic radiator. That's gain. And gain is a function of the angle theta and phi, and there is something they always call, or directivity is a function of theta and phi, and they always say D max is the thing we actually look at. So D max is the greatest possible value it has. Just remember that. Now, I'm going to go through a simple calculation using this concept for a short dipole. Then what I'm going to do is give you a more reduced formula that makes it easier to do this. And this should be beneficial. But first, we're gonna do it based on that concept for just a short dipole. And you don't have to write this down, but please watch. Because it's important that you get an idea how this works. So let's say we have a short dipole, like this. I'm gonna orient it in the z direction, and I'm gonna go ahead and put a current I on this short dipole. That means at any range where that's theta r, that I'm gonna have an actual P av that I can calculate. And the average power density here would be equal to 1/2 the magnitude of the E field squared divided by intrinsic impedance of free space, and it would be in the A to R direction. I hope you understand that that's just the general formula for a propagating wave. 1/2 E squared over A to naught, power density. You agree with me? So now what is the E field for a short dipole? This P av here would become 1/2 divided by A to naught. For a short dipole, the actual E field is equal to J. We don't care about that because it's a phase term and that's a magnitude squared. J, and then it's eta, beta, and it's I, then it's times L over 4 pi R, right? 4 pi R squared, or excuse me, 4 pi R, pardon me. And then there's a phase term, e to the minus j beta r, and then there's the sine of theta in there, and it's in the a theta direction, that doesn't matter, squared. And it's in the AR direction. Does everybody agree with me there? Right? I mean, that's just the short dipole, that's the field for it, right? The electric field, and I'm squaring. Now, I gotta tell you this, the e to the minus j beta r, that's like e to the j 40 degrees, minus 40 degrees, something like this. E to the j anything is it's got a real imaginary part, but its magnitude is always 1. Do you all agree with me there, class? And because of that, we can get rid of it, because we're doing a magnitude squared, really. So just get rid of that. Now, this is the nuts and bolts of it. That's the average power density, right? So I can collapse that down to what? I can say that's really 1/2, I've got an eta squared and 1 over eta, so it's 1/2 times eta naught. Then it's times beta L over 4 pi, all squared, those are squared. And then I have a sine squared theta divided by r squared. And that's basically n times, I should have put the I in here too, I squared. Are you with me? We did this before. So this is a constant. And we can just call that K. We're going to do this again. Are you with me? That's some constant times sine squared over r squared. You'll see it'll be a different constant for a short loop, but the short loop will always have a sine squared over an r squared term for power as well, as long as the loop's oriented to the xy plane. Now we take this, and I'm going to call that K, and I want to find the total power radiated. So P radiated is equal to the integral, it's a double integral, of P radiated, which is my K, right, times the sine squared of theta over r squared. That's the power density, and it's times the differential surface, right? I've neglected the AR direction. You could put AR here. And then the differential surface, do you remember what a differential surface is in spherical coordinates? This is on the outer holding r constant. What it is? Anyone? Well, it's what? R d theta times r sine theta d phi. Or, better said, it's r squared times the sine of theta times d theta d phi. Do y'all remember that? For the outer part of the surface, and it's in the AR direction. All right, where does theta go from? We did this integration, most of you remember. Where does theta go from? North pole to south pole, from 0 to, exactly, from 0 to pi. 0 to pi. And where does phi go from?
0 to 0.
Remember that. I think people make mistakes on it. One of the interesting things you see right away is AR dot AR is 1. We did this integral, so I'm not worried about it. I'm just making sure you understand what we're doing. So AR dot AR is 1, I get rid of that. Now you'll also know that there was an r squared term there, right? It's r squared sine theta d theta d phi. You'll notice the r squareds cancel. Does everybody see that? So they cancel. So now basically I have, and that cancels, I have k sine squared times sine theta d phi. You remember when I had this integral, what I did to sine squared, anybody? I know you know this, it was a trick. I made it 1 minus cosine squared, right?
Yeah, then a u substitution.
Then let u be equal to cosine theta du minus sine theta, right? And when you do the integration, the whole thing, I know the integral of phi from 0 to 2 pi is going to be 2 pi. That I know. And I also know when I do this integration, the remainder of this theta between 0 and pi, I get 2. This I know because I've done it too many times. So the upshot of this whole thing is I get k times 4 pi as p rad, and k is over here, right? And then, I don't know if you remember this, I found something called the radiation resistance, right? And I found the total power radiated. I'm just going to put it down. This total power radiated, once you go through and put it in, eta naught is 120 pi, and beta is 2 pi over lambda, and you break out lambda over L by itself, you end up with this. And correct me if I'm wrong, 40 pi squared, and then it's L over lambda squared ohms. Or, excuse me, times I squared. Is that the total power radiated? Could somebody take a look at that? And it's what? 1/2 I squared R rad, right? And R rad is 80 pi squared L over lambda squared, isn't it? Just take a look at this. Does he have this for P rad anywhere? Mm-hmm. And it should be in watts. You agree with me?
Yeah.
All right, we're almost there.
444.
Page 444? Okay, check there. Make sure everybody sees where this is, so you understand. So that's total power radiated. Now with that, what is the isotropic radiated power? P av iso would be equal to what? Well, it's that total power, right, divided by what? The surface area, 4 pi r squared, isn't it, class? If that's the power that's radiated, all of it, if we divide it by the surface area, we get the power density, don't we? So if we take this and we divide this right here and we divide it by the surface area, 4 pi r squared, we go ahead and we get the average power density. So that's 40 pi squared L over lambda squared I squared, and then divide this by 4 pi r squared, and now I have the isotropic power density. Do you agree? So we started with the equation for the electric field. We get the average power density, then we integrated the average power density over total spherical surface to find the power radiated. And now, if we wanted to replace that antenna with an isotropic radiator radiating the same amount, this would be the field, or this would be the power from that, right? So now we can go ahead and get the directivity. I'm going to do it here. Now I can say the directivity as a function of theta and phi, R will not be part of this, is going to be the actual power density right here that's radiated by the dipole. I mean, by the short dipole, right? This is it, correct, class? And you'll notice it becomes 1/2, and then it's eta naught, right? Beta L over 4 pi squared. Actually, it's eta naught. Sorry, let me do it this way. Eta naught over beta L over 4 pi squared. I'm gonna break I squared by itself out there. Then it's times sine of theta squared, and it's divided by R squared. Now I take that, so that's the power density from the actual electric field from that antenna, and I divide it by the isotropic power density. So it's 40 pi squared, L over lambda squared, right? I squared, and it's this divided by 4 pi R squared. Now, I want you to just watch this for a second with me, just so you see what I'm doing. This is the formal way to do it. Does everybody see the R squareds cancel? This 1 over R squared comes up here as R squared, it cancels. Do you all see that? So I'm going to erase that. Now the next thing I'm going to do is say, if you take a look at this right here, the I squareds cancel. Does everybody see that? Now, after that, I'm going to start reducing things as easily as I can. When this 1 over 4 pi comes upstairs, it's 4 pi. Do you agree with me? So I'm going to get rid of this 4 pi and take one of those out by itself. So there's a 1 over 4 pi here. Agreed? Class? All right, now that I have that, I'm gonna try to do this without too much of a problem. Does everybody see the L's cancel? Links cancel. So I get rid of that. Now beta is 2 pi over lambda, agreed? So now I'm gonna replace beta by 2 pi over lambda. And does everybody see the lambda squared is going to cancel? When I take lambda squared upstairs, it becomes lambda squared divided by lambda squared, it goes away. Does everybody see that? So get rid of that.
Pi squares.
You're going to see a lot of cancellation. Next, you see the pi squared cancels. One other thing too, that becomes a 4, doesn't it? I'm going to put it in there. So now I get a 4 here. We're almost there. All right. Here, at this point, I'm going to just write down. How about we do this? Okay. Now I'm going to write the whole thing down. It's left. So I have 1/2. Eta naught is 120 pi, right? It's divided by pi, right there, and then divided by 1 over 40 pi squared. I hope you see, the only thing I've done is take all those constants out. I know it's times sine squared, but I want to just take all the constants out. Do you all agree with me? Can you see it, Josh?
Yes, sir.
All right, do y'all see what I'm doing? All right, now, follow me on this one. This is just me talking. You can do it any way you want. I'm going to get rid of this pi. I take 120 over 2 is 60. Now I have 60 over 40, correct? So that's going to be 3/2. And you know what? We missed the pi.
Yeah, you canceled it out. It's
Yeah, you're right. That should be gone. So really, we should get 3/2 times the sine squared of theta. And this should be times sine squared of theta. And that is the directivity for a short dipole. And it's also the directivity for a small loop. Are you with me? Now the gain is altogether dependent on the resistance, the DC, or I should say the high frequency AC resistance of the loop. Do you remember we used skin depth calculation to calculate the resistance of a short antenna? You remember that? And we calculated the efficiency by dividing what? R radiated by R radiated plus R high frequency AC. Do y'all remember that? That's the efficiency that we would use in the next calculation. The gain as a function of theta and phi would be equal to this directivity, really D of theta and phi, and it's also times the efficiency. So the efficiency is somewhere between 1 and 0.99, maybe 0.95 for a lousy connection. And then if there's an impedance mismatch or something like this, then it goes way down, but that's basically it. Follow me, class? Okay. That's gain in a nutshell. And in the book, he'll have several different patterns. All right, what he'll give you is the pattern factor, and he wants you to calculate this. And these are problems that are fairly simple. Now, I'm going to go through the next part. If you remember, I was doing the halfway, or the long dipole last time, wasn't I? Wasn't that the last notes from last time? Do I recall? All right, let me go ahead and recreate this. Did we get down to the electric field from a long dipole or not? I think I put that up there, didn't I? From any arbitrarily linked dipole. All right, now the integral on that's a nasty one. I think I mentioned the way to do it, use Euler's on the cosine, the actual cosine term, and once you do that, it breaks down fairly easy. But here's what you get for the electric field when you have a dipole that's long. So when the dipole's length L is of the order of a wavelength, that you have a current distribution on this, he shows in the book, that this is going to be I here, I of Z. I of Z is actually equal to some I naught, forget the phase angle, and then it's going to be equal to the sine of beta times L over 2 minus the magnitude of Z is the current as it's deposited on this, and this is the Z direction here, and this is centered at the origin. The current has to go to 0 at the ends of the antenna, right? And that means the sign of this argument. If you look at this, when Z is equal to L over 2, I have L over 2 minus L over 2, or 0. Sine of 0 is 0, isn't it, class? And it doesn't have to be a maximum at the center, and here's why. The longer that antenna gets, the deeper this actual, this notch will become. At one time, if you get it to a full wavelength, you'll have almost a null right there, and the impedance is very large. Do you follow me on this? But if it's a half wavelength is when we have the current at the center being a max. And there's reasons why you would want one or the other. Now from this, we said if we're at a range R, this is in Dr. Wentworth's book, we get an E field in the theta direction, and the E field in the theta direction is given as J60 over R. There's no L in it at all. It's times E to the minus J beta R, but then there's this that's going to be equal to the cosine of beta L over 2 times the cosine of theta minus the cosine of beta L over 2, if you look there, all over the sine of theta. Now that's the actual electric field. I think he has the electric field like this, but he may show this part, I don't remember exactly. Do y'all see this right here? Give me a page number where it's to be found in the book. Go look at the arbitrarily long dipole for he might only give the magnetic field. He might give only H, but if you multiply H by 80, you get the E field.
Is that page 450?
Is it just the H field?
Yeah, it's just that.
I don't like the H field. I like the E field. So put the E field down, and this is in the A theta direction. It's 60 over R, all right? I'm just telling you that. What does he have for H? Doesn't he have something like,
It's like J I naught over 2 pi.
yeah, but he has an I in there too, doesn't he? There has to be an I didn't put that in there.
Yeah.
It's J I naught.
What is this constant up in front of there for the A? Here's what I'm getting at. I know that eta naught times the H field will be equal, or the H field in the phi direction will be equal to the E field magnitude, right? So I know that that's 60. So whatever he has here, eta naught is 120 pi, correct, class?
Yeah.
So he has to divide 120 pi by 2 pi, so he has to have 1 over 2 pi in the H field.
He does J I naught over 2 pi.
Yeah, and I don't like that. I like this. I always remember it with the 60, and there's no length involved. That's the key. You see, there's no length of the antenna?
Yeah.
All right. I mean, there is right here, but I mean, it's not multiplying the actual I. Follow me? It's buried in the cosine arguments. Now, that's the general electric field for an arbitrarily long dipole that's actually center fed. Something about this I'm going to tell you that makes it interesting. That's not, if you take that, what I put there, and try to do an integral for that to get the total power radiated, in other words, try to do a surface integral, it's extremely difficult. And this is one of those things that they don't even talk, he doesn't even talk about in our text, I don't think. So we need that, why? Because we need the total power radiated to get the radiation resistance. Do you follow me on that? And what you see is the radiation resistance can become very large and very small. But he doesn't have it in his book, does he? Radiation resistance for an arbitrarily long dipole? There's a MATLAB exercise in the back, I believe, where he asks you to calculate it for certain
It
lengths.
says R equals 30 over pi F of theta max times whatever ohm D.
For an arbitrarily long dipole? Is that right? Or halfway?
It's just under dipole.
Which one are you looking at? I'll tell you why. Well, I guess.
The one he was talking about was this,
I don't know if that's.
but that F theta.
Oh, that's the
on
problem.
other side.
All right, now I'm going to
That's
tell
what
you.
he got up there.
That omega sub p is what he has.
Yeah.
That's called a solid angle. That integration is a bare and it's not a closed form solution. You follow?
Yeah, I see that.
So that's the reason for an arbitrarily long dipole, you have to use a anything that's arbitrary, you have to go ahead and do a numerical methods kind of approach. You have to use something like MATLAB and write a script to calculate that integration. It's not trivial. And I don't believe there's a closed form, but if I am wrong, I'll be the first to admit. However, from this electric field, I just want you to know this. We can always get the power density. Do y'all agree with that? Now, the way Wentworth's book is structured is this. He doesn't like talking about this in terms of an angular function. He likes talking about an angular function multiplying the power density. Are you with me on this? So listen to me here. What he says is, I don't care about the E field, but I care about is the actual power density that I call SAV of theta of phi R, or in his book he has it PAV. That's the actual power density. And he's going to have this down, when all is said and done, is, I want to say it's J, oh I'm sorry, no J, it's 30, I think he has, let me just think about that. Oh, or no, it's 15, maybe I'm wrong about this. I'm thinking the way he has it. Does he have 15 over pi squared times I squared over R squared times some F of theta? Is it in his book?
Yes, sir. Yeah.
Is it 15 over pi squared? This is for an
It's pi R squared. The pi is not squared.
Oh, I'm sorry. 15 over pi R squared and I squared up top. Do you all see this? This is for an arbitrarily long dipole. Do you follow me?
Yes, sir.
Now watch, this is important. This F theta isn't this. That F theta here is equal to this squared. So it's cosine of beta L over 2 cosine of theta minus cosine of beta L over 2 over the sine of theta squared. Now he likes that, which means this function could be replaced by the square root of F theta in his book. Agreed? I personally has always seen this defined as some angular function. They usually call this small f of theta phi. And if you'd like, you can say that this function here is, I'm going to call it small f of theta phi, and really large f of theta phi is just equal to magnitude of f of theta phi squared. And that way we'll be done with it. Agree, class? Now that's an arbitrarily long dipole. And typically, the dipoles that are of most interest to us at this point are a short dipole and a half-wave dipole. The reason a half-wave is so interesting is because you get gain about as good as it's going to get out of a dipole antenna. You have a driving point impedance of 73 ohms, and you can get rid of the imaginary point, which is nice. It's a nice big impedance. And to be frank about it, it's about as good as it can be for a wire antenna. Now I say that loosely because somebody's going to come at me and say, well, you know, when you have a folded dipole in certain areas, it gives much higher gain, and they're probably right. They are right, but at least for the purposes we're talking about, the half-wave dipole is probably the one that's of most interest. By the way, we're going to see in a second where we can get the antenna patterns where for any given arbitrarily linked dipole, we can take a look at how f theta varies with theta. One thing you'll always see is the power radiated up the antenna axis or down is 0. And the maximum value for the half wave, it's called broadside, it's when theta is 90 degrees. In other words, if this is the antenna, the max power is coming out in this plane. That's true for a half wave, it's true for a short dipole. If you think about the short dipole, we know it's sine squared of theta is the power pattern, right? Well, sine squared of theta is the maximum of that, same as the maximum for sine theta would be theta is 90 degrees, right? Or perpendicular to the actual antenna. You follow me, class? All right. So now we go from short dipoles. We're going to go to the second most common type of antenna that you'll you'll actually be involved with. And this is the half wave. Please write this down. Half wave dipole. This one's important, and you got to know a little bit about this. All right, for a half wave dipole, the total length of this antenna, L, is equal to lambda over 2. All right? It's still a fairly long antenna. And because of that, since it is a long antenna, the current distribution on it, if this is I of Z, it looks like this. And I of Z is some I naught here times the sine of beta. Now remember this, normally it's beta times the quantity L over 2 minus Z, but since L is lambda over 2, this is times lambda over 4 minus magnitude of Z. Does that make sense to everybody? The length is equal to it's lambda over 2. When you divide it by 2, it's lambda over 4. Where I'm getting at is just, well, I guess I didn't put it over here, but that's the expression for the current. Can you all see this here? And that's about what it looks like. It goes to 0 at the ends. Now, what happens is this. When we have this short dipole, if we're out a distance r away, and we want the electric field here, please write this down, because I think he has H field, and I don't like that. I prefer you have E field. For the E field, what you're going to get is this. You're going to see it's J, it's times 60, and there's going to be an I, there'll be an E to the minus J beta R, and then there's going to be an R here. Now normally, this power pattern comes next, or this small f of theta phi comes next, but here's what happens that's interesting. Remember that now L is lambda over 2. that means beta L is gonna be lambda over 2, or I should say beta is 2 pi over lambda times the length lambda over 2 is simply pi. Do you all see this, class? Because the length of an antenna is lambda over 2. Please, can you all see it? Remind me to hand back your quiz too. I don't think I did that. I'll do it when I'm done with this, all right? So that's pi. Now what happens over here? Follow me. Now I have beta L over 2, right? Beta L is pi over 2, 90 degrees. What's the cosine of 90?
0.
So we get rid of it here. And we're left with this, and this is just pi over 2. So this is E theta is this times cosine of pi over 2 times cosine of theta, all over the sine of theta. And that right there is my small f of theta phi. And it's in the A theta direction. Now you don't know what that looks like, but I'm going to tell you what it looks like. If you would plot that function, cosine of pi over 2 cosine theta over sine theta, I'm going to show you what it looks like. Looks about like this. If this is the angle, right, we're going to measure from. This is theta. And if the radial distance right here was proportional to f of theta phi, this is called an angular power plot. It's really called a polar pattern. You've heard this before, probably polar plots, right? So what we're doing is plotting some value versus angle, how it varies. Well, if you take a look at what this looks like, it looked like this. Where this would be the angle theta, and this value would be the value of f of theta. Phi doesn't matter because this thing, you spin it around the axis, it's symmetric. It doesn't matter what phi is. Do you follow me, class? It radiates the same for a given theta for any value of phi. Now, so we've got that. If you would actually plot on top of this, the pattern, if this is f theta for the half-wave dipole, if you would plot f of theta phi for the actual short dipole, you would see it's just a little bit broader, like this. Just a little bit broader. Which means one thing to us, which is the nice thing to know. It means if we take this, and then the next thing you get is P-Av from here, and we can get that as 1/2 magnitude of E squared over eta naught. You agree with me, we could get that, correct? And then we would have this squared, correct? And that would be what? I think he has it there. That's 15, right, over pi r squared times I squared, and then it's times this squared. Now, if we took this and we integrated it around the surface of a sphere, just want to make mention of one thing. When we do that, you see how that 1 over sine squared is there? It would cancel the sine squared and the differential surface. The r squared sine squared theta, d theta, d phi, do y'all remember? But when all is said and done, when we go ahead and we integrate P-Av dot ds over the surface, closed surface of a spherical shell, what we get is the radiation resistance of the antenna, R rad, over 2 times I squared. And for a short dipole, R rad is 72.3 ohms. Take a look at that and see if you see for a half-wave dipole, radiation resistance is 72.3 ohms.
73.2.
73.2, sorry, 73.2, okay. My, somebody, I got a comment about this too. That's not exactly true. Here's why. The radiation resistance is a function of the diameter, or really the radius of the wire, or diameter. And the bigger the diameter, the more it changes, the more the inductive component. Now there's something else I gotta tell you. The actual impedance of an exact short dipole, or a half-wave dipole, write this down. This is, I want you to make sure you see this, make it explicit. He mentions it in his book, you have to know this. For an exact, underscore that, short dipole. The actual input impedance is equal to 73.2 plus J 42.5 ohms. Now, he'll have that. And that's not quite true either, because this is really neglecting the effects of the radius of the antenna, because the bigger the cross-sectional area of that wire, the more the change from there. And I'm going to tell you, it becomes a very interesting problem. This gives a very good approximation for something like this. Suppose I go down to the shop, or better yet, I take a paper clip, all right? I take a paper clip, I don't want paper. I want something with less bent in it. I forgot. You know those rods that you use to keep plants straight? They're made of aluminum, I think. Well, if you took one of those rods, right? You took a rod, I don't know, like that, and you literally secured it to, say, a yardstick, and then cut it in the center, and made it exactly a half wavelength long for some frequency. And you went ahead and you measured the input impedance of that antenna at that frequency, you would get close to that right there, guaranteed close. But here, and this is some, I wish I could do this with you guys. So we've got an antenna that's got 73.2 plus J 42.5 ohms. We would like to get rid of this. You know why? Because that J 42.5 has to do with near field inductive energy that's never launched. The only thing we care about is launching electromagnetic energy with that antenna. Follow me? So, how could we get rid of it? Well, we could put in series with it a capacitor that had an exact impedance of minus J 42.5. That would get rid of it, and there we'd have only real impedance, right? And that means for a given voltage, I could have the most current going through there, and therefore the most current, most power. Or I can do this, and this is a neat thing. If you go and you clip the ends, the very ends of that antenna down, and you need to do this carefully, but if you start clipping them down, what you see is that value starts shrinking. And when you make L, and you should have this, about 0.49 lambda, you should have this, you get a Zn equal to 73.2 plus J0 ohms. Just by clipping it down, instead of making a half wavelength, make it just a little less. And guess what? The directivity doesn't change appreciably, or the gain. It's almost the same, virtually, I just can't tell, but you get rid of the J 42.5 ohms. Do you see that anywhere in his book where he says this? Yeah. What page is it on? 460. And it's in the middle of the paragraph?
Yeah.
Does he have the link that 0.49?
0.485.
All right, 0.485. And that's radius dependent. You can put 0.485. 0.485 lambda. I've never done that, by the way, but I teach EMC, and this is one of these tricks that you know about. If you ever need to get an antenna matched, and you don't want to spend the time going and getting another part, so the reactive element, that you choose will have an impedance opposite the impedance that would have when you could put them in series. Follow me on this, guys? You can just start cutting down the ends of the, it's really easy to do with thin wire antennas. When you take a thin wire and lay it on a yardstick and tape it down, then when you measure the impedance, you can take just toenail clippers work fine. You can start knocking off the ends little by little. When you measure the impedance, you'll see this part going down, down, down. Finally, it's about gone, which is kind of a neat thing to do. All right, now, this is the half-wave dipole. The one thing I didn't mention is the gain of it, or the directivity. When you go through this calculation, if we wanted to, I'm going to just mention one thing about this, because here we're going to do the calculation a little differently. I told you before how the fundamental theory of calculating the directivity antenna is done. I mean, fundamentally, you find the actual total power radiated, then you say I'm going to create an isotropic radiated power density, and I'm going to use that isotropic radiated power density and divide it into the actual power density for any angle, and that's my directivity, right? That's fundamental. An easier way to do it is this. You simply say directivity, all right? This is directivity. And call this max directivity. And I'm going to make a few points here. The maximum directivity will be equal to 4 pi divided by what's called the solid angle, omega sub p. So omega sub p is the solid angle. Now, what is the solid angle? Well, the solid angle is based on a double integral, and it's the normalized power density of theta phi. So whatever the power density is that you come up with for any of these things, what we do is we normalize it. We find the maximum value of it, and we divide it into the power density to find the normalized power density. When it says normalized, it means the maximum value is 1, usually. Does that make sense to everybody? Then you take that and multiply it by sine of theta d theta d phi. Now this right here, the symbol is usually d omega, because the units are a steradians, or it's a solid angle. Have you heard steradians before? There's radians are what? Measures in one dimension of change in azimuth or elevation. Steradians are two-dimensional. The total spherical surface of any sphere has 4 pi steradians, because if you integrated r squared sine theta d phi, you would get 4 pi r squared would be the surface area, right? And then if you get rid of the r squared and normalize it to r squared, 4 pi is the actual number of steradians in a surface. 4 pi steradians. And that's really, I forgot what how that converts to degrees, but, degrees squared, but really, that would be, (360 squared degrees). Right? But don't worry about that. Now, when we integrate this, theta goes from 0 to pi almost always, and phi goes from 0 to 2 pi almost always. The reason I say almost always, there's going to be a case when we actually use the ground plane to reflect energy, and then we don't have a dipole, we have a monopole, and this angle will be cut down from 0 to pi over 2, and I'll get to that though, all right, time. So this is the actual omega sub p. Now for R's, when we go ahead and we do this integration, well, let's see. That's the power density, right? The maximum value of this function, cosine squared of, cosine pi over 2 cosine theta over sine theta, that whole thing squared, this has a maximum value of 1. It's just like sine squared, follow me? So that means when we normalize that, the only thing we're going to have is that function. If we were to do that integration for the half-wave dipole, it would be the integral from 0 to 2 pi, integral from 0 to pi of that function squared, that function right there, normalized, or simply the cosine of pi over 2 cosine theta divided by sine theta, that whole thing squared, times the sine of theta, d theta, and I've got a comment about this. You see that this is a sine squared here? Times the sine would leave me as 1 over sine, right? Then you would have a cosine in there. That integration is still non-trivial. The way I would actually do it, maybe you wouldn't, I would bring that down to simply 1 over a sine there, and then I'd use Euler's on this. I'd break it up as e to the j pi over 2 cosine theta plus e to the minus j pi over 2 cosine theta divided by sine theta, right? It'll be that squared, and then you have to square the dang thing out. But I would break that thing down, and I might even use a half angle. Let's see, cosine squared cosine of 2 theta is, no, cosine squared is what? 1 plus cosine 2 theta, cosine squared theta is 1 plus cosine squared theta over 2, but don't even worry about that for now. There's different angular ways to do tricks here and get it done. What I wanted to say is this thing right here will give you the solid angle. We don't have to do it. But here's the important thing. When you do it, you get this value for D max for a half wave dipole. Please write this down. You find out this to be 1.76, or I'm sorry, 1.64, pardon me. 1.64 is going to be D max for a half wave dipole, for half wave dipole. Do you see that there?
Yes, sir.
Now, a lot of times they don't give the directivity or gain in terms of what I call the linear value. They'll take the logarithmic value. So if you look at that in logarithmic value, it'll have 10 times the log of that, and it'll be 1.76 dB. Do you see that anywhere? You have a calculator? Do this calculation. This is D, and this would be in dBi. dB with respect to isotropic. 10 times the log of 1.64. Tell me what you get. I think it's 1.76. No?
2.1.
You're right, sorry. You are absolutely right. For this one, it's 2.14. I'm so sorry. 2.14 is the gain in dBi, or the directivity in dBi for a half-wave dipole. My bad. Now remember for a short dipole, this is D max for half-wave. For a short dipole, D max for a short dipole we figured out was what, 1.5 or 3/2? You all remember that? And then in dBi, what would it be? So dBi for a short dipole would be 10 times the log of 1.5. That's 1.64, I believe. My bad. Is that right?
Yeah, I got 1.76.
Or I'm sorry, 1.76. 1.76. These are things, this is 2.14, 1.76 dB is what they sometimes list. When they list gain in a lot of applications, book and manuals, it's in dBi. It's dB with respect to isotropic. So it's 10 times the log of the linear gain. Now the one I usually remember is the linear gain. For a short dipole, the linear gain is 1.5. For a half wave, it's 1.64. Not a whole lot better. The real benefit to a half wave dipole is not the gain, but the input impedance goes up to 73.2 ohms. And then you can do various things to get rid of that imaginary component. Just shorten it a little bit and gets rid of it, okay? So that's sort of, that's dipole in a nutshell for you, all right? Now, there are a variety of other antennas. I'm gonna show you some more stuff with antennas now that's beneficial. You know, gain is really the thing that everybody uses. They don't use directivity. Directivity times the efficiency is the gain. That's what everybody uses. Now, please write this down, because this is important. So, no matter what antenna you have, doesn't matter if it's made of a straight wire, or if it's a circular loop, or if it's a parabolic dish antenna, like the satellite dishes that you see on the housetops, or if it's a bunch of patch antennas in an array structure, it doesn't matter. The overall antenna has a quality that can be calculated called the gain. And by doing various impedance matching techniques, you can get a maximum power transfer to it. But here's how gain really works. Let me show you. Suppose I have an antenna here and I say I have a gain of, I'm gonna say, 30 dB. They use something, oftentimes, with antennas you have patterns that look like this. Please try to understand, I'm covering some material that I don't have time to get into depth. Instead of having, remember with the half-wave dipole, what did we say it looked like this, right? Right? Well, you're gonna see as you increase the length of that, all of a sudden this pattern won't look like that. But as you increase the length of the dipole, all of a sudden it'll look like this. It'll look like a figure 4. Now, there's 2 lobes here, right? You keep on increasing the length and all of a sudden, this is just for a wire, straight wire antenna, and you'll get this. You'll get a couple of them that are very large. The large ones, the things that stick way out, are called a main beam, or main beams. This small one here and here, these are called side lobes. Now usually you have only one main beam. Everything else is called side lobe. Follow me? But the main beam's the thing you worry about. It's what you focus on. So I'm going to say I have an antenna that's got 30 dB of gain in the main beam. And the main beam's pointed in a direction called the bore site. Now, have anybody here ever used a rifle, BB gun, anything like that? Right, when it comes, a pellet comes right out of the bore of the gun. The way it's going, that's called the bore site. It's like the intended path of the thing, right? Well, the bore site for an antenna is the intended maximum direction of radiated power, the bore site. And for a wire antenna, for a half-wave dipole and short dipole, it's perpendicular to the wire's direction. But it's different for different antennas. For parabolic dishes, it's also always perpendicular to the center of the parabolic dish. It's pointing that way, like a reflective mirror. For other types of antennas, things called Yagis, that we'll learn about later. You'll learn in antennas and log periodics, not so. It's a combination of things. But just realize that's what you worry about is the bore site of the antenna. And when you have this, if I have a gain of 30 dB, now listen to me on this problem, this is an important one. That's the bore site, right? And I'd like to know at some radial distance R what the power density was. So what I want to know is what P average is down here in the bore site, or better yet, for any angle. Now please watch this. So the way gain can be used to get this, if you have an antenna where the gain is defined, usually the max gain times some angular pattern, you can say that that P-Av value, please watch this and write it down. P-Av right here is a function of R, theta, well actually, forget that. Here's how it works. The actual P-Av will be equal to the total power radiated, P radiated, times the gain of the antenna, and gain is usually a function of theta and phi, that's the way it is, divided by 4 pi r squared. And here's how gain really works. I want you to listen to me. If you have an isotropic, assume you don't have any gain at all. If you have an isotropic antenna, if I take total power radiated over 4 pi r squared, that's the power density at any range, right? When you multiply it by the gain, it tells you what it really is for this because of the focusing ability of the antenna. So that's why gain is so important. It automatically gives me the power density at any range for any theta and phi. All right? I'm going to give you the reason I put 30 dB down. I want to do this with some dB calculations involved. Now, here's the problem set before you. I don't want just this. I want PAV. This is what I'm looking for. I want the E field strength. So I want two things. For an antenna, here's my antenna. It's got 30 dB of gain. It's got a transmitted power equal to 1 kilowatt. I'm at a distance R equal 10 kilometers. And I want to know first the power density in the bore site. This is in bore site. And I also want to know the E field out that direction. So now we're going to use the gain to get this. All right, this is going to be a gain of 30 dB in the bore site direction. So I'm how far is 10 kilometers in miles, by the way? Anybody ever do a 10K race? 6.6 miles, isn't it, class? 6.6 miles. Anybody run a 10K? 5K?
Ran a 5K one time.
All right, that's 3.3 miles. So, I mean, this 10 miles, by the way, things that are increment 10 miles sections are easy for you to understand. You've got a pretty good idea how far 10 miles is, how far 100 miles is, right? So you can do the conversion to kilometers fairly quickly. Or sorry, 10 kilometers is 6.6 miles, 100 kilometers is 60.6 miles, and so forth. And it's a good kind of reference. Anyway, I'm out 10 miles, or sorry, 10 kilometers or 6.6 miles. So that means my average power density would be what? Here's where you got to take this gain and put it back into the linear. Well, gain in dB, write this down, is equal to 10 times the log of the gain in linear terms, the linear value. All right? Gain is related to power. Remember, anytime we deal with dB and its power-related terms, it's 10 times the log of that. Do y'all remember this, class? So let's calculate this. If I have 30 dB here equal 10 log of G, what do I have? I've got 3 equals log G, right? That's log base 10. Or I have 10 to the third equals G, or 1,000. Don't I, class? Agree? So that means for PAV, I would have 1,000 or 10 to the third. That's the gain, and I'm going to put the gain first, times the radiated power. I said that's 1 kW. 1 kW is 10 to the third as well, isn't it? A kilowatt is 10 to the third watts. Then I'm going to divide it by 4 pi, and my R squared was 10 kilometers, or that's 10 to the 4th squared. So what do I have? That's 1 over 4 pi, right? Then I have 10 to the 6th over 10 to the 8th, or 10 to the minus 2, and this would be watts per meter squared. So what is that? 10 to the minus 2 over 4 pi is what? Anyone? I'm trying to make this easy for you, I promise you.
0.8 million.
0.8 times 10 to the minus third watts per meter squared. Y'all agree with that? 0.3 milliwatts per meter squared, roughly? Now, how do I get the electric field if I have that? That's the power density. How would you get the electric field? This is where people trip up on quizzes. Oh, no. You're right. I would say that the actual power density, PAV, is equal to 1/2 magnitude of E squared over eta naught, right? Agree? So if I wanted the E field, I would take the average power density, multiply it by 2, and by eta naught, and take the square root to get the E field's magnitude. So in my case, what is that? It's the square root of 2 times 120 pi times 0.8 times 10 to the minus third. And what do you get for that? I'm curious myself. Boom. Anything?
0.77.
So we have 0.77 volts per meter for the electric field. How would you get the H field, anyone? Got the E, how do we get the H? Propagating field, guys? Divide by eta naught, right? Divide by 120 pi, correct? H is amps per meter. E is volts per meter, right? If I've got volts per meter and I want amps per meter, I gotta divide by ohms, don't I? Ohms is eta naught, intrinsic impedance. I hope this is helpful. So, needless to say, now I have the electric field, and you've got a taste of how gain is useful for antenna calculations. That's how it's really used. You buy an antenna with a certain gain, it gets it. Problem with this is the higher the gain, almost invariably you have side lobes you don't want. So there's tricks to make the antenna so that the gain will be a maximum in the main lobe and the side lobes will be 30, 40 dB below the main lobe, and that's not bad. That's 1,000 to 10,000 times less than the main lobe, which means the power there is 1,000 to 10,000 times less the power of the main beam. That's what everybody wants. But this is interesting. We're going to keep going on a few things here. Now, finally, I'm not going to have time to do arrays, but I can do one thing that's important. It's called, I think, a Friis equation. Friis transmission equation. You're going to like this, I think. I hope. Now, I'll do arrays next time. But this is the Friis transmission equation. All right. Now, here's the deal. Here's how this works. Suppose I have an antenna here, and it has a gain. All right. Then, I'm separated by some distance r. And I have another antenna. Call this G of the transmitter. This is the transmitter. And this is the receiver. So power comes up here. This is power transmitted. And this is in the bore site, so make sure you put down bore site. It doesn't have to be, but for this calculation, we're going to use bore site. It's a distance r away. There's the receiver. That means there's an actual gain of the receiver. There, I'll call it just GR. And the question is, how much power is received by that antenna? Which is a legitimate question, wouldn't you say? So here's how this works. Now, I want to say one thing. This doesn't have to be in the bore site. It could be at any angle, any azimuth, any elevation, but I'm going to use the bore site so we can use G max, all right, the maximum gain here. When you take a look at this, if I've got transmitted power, PT, comes out here at any given range, the power density, Pab, would be equal to the transmitted power over 4 pi r squared times simply the gain of the transmitter. Does everybody agree with that? Now that power density is in watts per meter squared. So it's power per area. Now it's gonna come and it's gonna strike this antenna. So the question is, how electrically big is the catcher's mitt that this antenna has? How much power will it catch, right? Without going, I don't have time for the details, but the term we use for this, the electrical area, is called the aperture. Aperture of the antenna. And the aperture of the antenna's symbol, I think, is AP in Dr. Wentworth's book. It's the aperture of the antenna, but write this down. Aperture of the antenna is lambda squared over 4 pi times the actual gain of the antenna. Gain of the antenna. Now this is a relationship between gain and aperture. Do you see this in his book? This is a Friis transmission equation section. It's further on. It's past the section on arrays. Just, you see it? Any page number?
I mean, it starts on 476, but I don't see aperture.
You're gonna see A sub P or A sub E, one of the two.
Oh, it's on ACB.
A sub E, alright. He uses E in his, I guess.
Well, he calls it effective area.
Yeah, that's another version.
Okay.
It's really the aperture, effective area.
Emacs.
It's actually the aperture, it's the size, the physical size. I mean, sorry, the electrical size. Now, this is equal to lambda squared over 4 pi times gain. Do y'all see that? So, when I look at this, the amount of power received by this antenna, it's actually gonna be received by the antenna, will be equal to the aperture times the actual power density, times PF. Now, here's where I go ahead and I put it all together. So aperture is lambda squared over 4 pi times gain of the transmit, or gain of the receiver, right? Then power density is PT times gain of the transmitter over 4 pi R squared. Does everybody see what I've done here? I'm saying, yeah.
So instead of the gain, the book has D max
All right.
with the effective area.
I put gain because he's assuming an efficiency of 100%. You could use D there too. I'm using gain because gain means it's a truer value of the actual amount itself. Now this is the Friis transmission equation. If I take the received power and divide it by the transmitted power, I get the transmitted power out. What you're going to get is this. You're going to have lambda over 4 pi here squared, and then he's going to have gain transmitter, gain receiver, and he'll actually have just R, I think, in there. He'll have lambda over 4 pi R squared times gain transmitter, gain of receiver. Or in this book, D, I guess. They use D max, they use D1, D2. Is that what you're saying? What equation is that?
8.115.
You see it in 8.115, everybody? So this is the Friis transmission equation. And what it does is say that if you have a microwave length, this is one of the things that can be used for. Microwave length is just really something that communicates information between one tower and another. You've probably seen these things. Microwave links are used all over the place. They're just little repeater amplifiers, so a signal, you don't have to stretch cable from one area to the other. They just have a little microwave dish that sends a signal and another dish catches it. If I know the range, I know the gain, then I know the ratio. I really could take a look at the ratio of received to transmitted power. And you can take this ratio right here. Now look at this. If you get dB gain of 30 dB in each antenna, that's 10 to the 6th, right? 10 to the 6th times this quantity can be significant. What if it's 40 dB? That's 10 to the 8th, right? 10 to the 8th times this quantity can be significant. Now, something I'm going to tell you, you can never get more power out than you put in. But there are tricks you can do with that equation that makes you think you can, and here's why you can't. You see this gain? Gain is related inversely to lambda. All right? gain squared the two gains together is the inverse of lambda squared. So I'm going to tell you, you can't ever get more than you put in, no matter what the equation says. Because here's the other thing, people say, well, we need more. This is one of the things at least I can think one person would say to me. Well, look, if we let R get less than 6 inches, all of a sudden we got more power than we put in. Yeah, this equation breaks down long before that happens. Now you're in the near field, and all the assumptions are out the window. So just remember that. You can never get more power out than you put into any kind of a standard passive machine. Passive out. All right, I'll give you some homework there. Does anybody have any questions? It kept it 2 minutes long. Y'all see this stuff? This is fairly casual. So if you got questions, let me know. Did y'all do the homework I gave you? Or at least look at it? No? Well, please do, because the bad thing about this is it all snowballs. Everything's built in this antenna section. Everything's based on the last stuff. That kind of can really bury you come Friday.
Do you have any quizzes from last week?
I do. Let me hand it back to you. Thank you. Here, I keep your quizzes on this side.
Do we have class on Friday?
I don't know. Is that mini master break or something?
Yeah, it's
It's
final
final exam.
exam day.
We don't then. Is anybody here in the mini master? I can't get, then we're gonna have to cancel class. I guess I'm gonna have to cancel my other class on Friday. I don't wanna give you a quiz on Wednesday. But I'll tell you what I might do. I might give you some homework that's not in the book and I'll collect and grade it. Alright? I'll give you some, I'm not gonna make it hard. What I'm gonna do is make it something where I'm trying to challenge you a little bit so you don't bore yourself to tears. Just looking at the solutions.
So you're saying it'll be due this upcoming Wednesday?
Yeah, it'll be like a quiz grade if you don't mind. I can give you a quiz, but the problem is I haven't gotten to the depth of material that I want. Alright, let me give you your quizzes back. Josh, send me an email reminding me to do that.